Good morning. My name is Divya Pradhan, and I'm going to be talking about action potential. The function of the neuron is to receive, conduct, and transmit signals. Neurons conduct electrical impulses or signals by using action potential. In simplistic language, what we are saying is that these nerve cells are going to transmit information or signals in a special format, and that is called the action potential. An action potential can be defined as a momentary change in the electrical potential on the membrane. Notice that I'm going to be talking about the membrane, not about the entire cell, but the membrane. Now, what is potential difference or electrical potential difference? What is this word, electrical potential? If this is a cell, and if there is a difference in the distribution of charges inside and outside, outside is positive, inside is negative, you will create an electrical potential. So, as I said, an electrical potential can be defined as a momentary, a brief change in the electrical potential on the membrane of a neuron or a muscle cell. And when this membrane potential changes, it results in the transmission of the electric impulse. So the change in membrane potential is brought about by the opening and the closing of certain ion channels, allowing the flow of positively charged ions across the neuronal membrane. Action potential in neurons are also known as nerve impulses, or spikes. And when a neuron emits an action potential, it is set to fire. Not really set on fire. The central players for this transmission of the signal are the voltage-gated channels. So, I will explain more about these voltage-gated channels in just a minute. Now, you need to understand that the axon is the only part that is capable of action potential. The cell body and the dendrites are not. These are not responsible for generation of the action potential. It's only the axon. All right. So, let's look at the stages of action potential. Neurons, like any other cell, maintain a difference of concentration of certain ions. Now remember, let's go back. Ions are nothing but charged particles. We need to understand this. Okay. And neurons, like all cells, have positively charged particles, that's sodium outside and potassium inside. Okay. So here what it is they have, in addition, they have pumps that pump in positively charged potassium ions. So unlike other cells, they have more potassium on the inside and more sodium on the outside, maintained by these pumps. Okay? The neuronal membranes can do so because of certain channels. Remember, we talked about voltage-gated channels. And these channels are they form pores. So here is a good example. So here is a channel. There's a protein which has a pore as a channel. So here what happens is particles can go in and go out. However, these are gated. If you notice that there's a gate in here. And this gate will open and close depending upon the voltage. So that's why these are called voltage-gated channels. Now, however, the sodium channels will allow only sodium to pass through, and the potassium will allow only potassium to pass through. This is something that you need to understand. Now, the first stage is that of rest. At rest, then the axon is not transmitting the message. At rest, like I said, there's sodium outside, potassium inside. However, some potassium leaks out of the cell. And when it leaks out, then what happens is there is no inward leak of sodium, but there's outward leak of potassium. And that means what happens is there is a difference in charge distribution. So the inside of the membrane is more negative than the outside of the membrane. Okay? And therefore, the cell is said to be polarized, and it has a voltage of minus 70 millivolts. Voltage is always measured in the form of volts. In this case, it's minus 70 millivolts. Now, what happens for a message to pass through? It has to cross over the threshold limit. So when a stimulus arrives in this membrane, which was at resting potential, it causes some sodium to open, and what happens is enter the cell. So some sodium starts entering the cell. Okay? So here's the cell. Remember, sodium is outside, potassium is inside. Some potassium has leaked out, so there's potassium outside too. Outside is positive, inside is negative. So when the information arrives, or a stimulus arrives, some sodium enters. So what's going to happen to this voltage? This voltage is going to change. If the stimulus, so more the stimulus, more the sodium channels open, and what happens is more change will be in this voltage. If the voltage changes from minus 70 millivolts to minus 55 millivolts, then only the message will be transmitted. Therefore, the threshold limit is minus 55 volts. A good analogy would be the toilet flush. You cannot push it very gently, otherwise the toilet will not flush. You have to push it to a certain extent, then only there is the flushing of the water. So like I said, that if the stimulus is strong enough to change the voltage, then only the message is transmitted down, if you remember, the axon hillock, down the axon. Otherwise, the message is discarded. So what you need to understand is the degree of this change is proportional to the intensity of stimulation. More the stimulation, more the change, and therefore what happens is the message, more chances of the message being passed down the axon. If it is a weak stimulus and cannot change the potential, it is not going to be conducted down the axon. So if the membrane potential crosses, once again to repeat, the action potential is generated. So now we go on to so like we said, the first phase was that of the polarized state. Now if it has crossed the threshold limit, remember it is going into the third stage, and that is all the sodium will now open, and all the sodium is going to rush into the cell. Okay? So remember, the inside had potassium. Some potassium had leaked out, not all. Majority of the potassium is still sitting here. So now all the sodium leaks in. Sodium has a positive charge. So what's going to happen? The inside now of the membrane is going to become positive, more positive than the outside. Therefore, what happens is the cell is going to go into a state of depolarized state. And the voltage will now go up to 30 millivolts. So the outside is negative, the inside is positive. There is the reversal in polarity. Because of this reversal in polarity, now the sodium channels which were open now will close. So no more sodium can flood inside. The next phase is the repolarization. So repolarization, now what happens is, the potassium that was sitting in, and the sodium, remember, has gone in, the potassium channels will open, and the potassium is now going to diffuse out of the cell. The potassium channels are the slower channels. Because of the change in polarity, remember, sodium channels closed after sodium all flooded in, and potassium channels open, so potassium is going to go out. And because potassium leaks out, what happens is the polarity is set again back, and the outside becomes positive, inside becomes negative. So potassium leaks out, sodium is still inside the cell. Sometimes this rapid diffusion of potassium will actually cause an undershoot. pushing the voltage which had gone from minus 70 at rest to 30 when it was depolarized down to minus 77 millivolts, which is lower than the initial minus 70 millivolts. This is called the undershoot. And because of this, what happens is, because of this change in the voltage, now the potassium channels will close. But again, we have to restore the membrane back to its original distribution. If you remember what we started out with, sodium outside, potassium inside. Now what has happened? Potassium is outside, sodium is inside. So now what happens is that in this state, the neuron will not be able to transmit any impulse, even though an impulse is coming and crossing the threshold. It will not transmit. Why? Because potassium is outside, sodium is inside. We have to get back to the resting stage when what happens is sodium is outside, potassium is inside. For this, now there are the sodium-potassium pumps. And these will use ATP to pump the sodium out and potassium in. This is called the refractory stage or period. And this can be defined as a brief period following the passage of an impulse, when an impulse that has exceeded the threshold stimulus will not trigger to be transmitted down axon, and lasts about 1/2500 of a second. This, now what happens is this changing, this switch in the membrane potential, from where? From minus 70 millivolts to 30 millivolts back to minus 70 or minus 77 millivolts. This change, this switch will cause, what happens is, this is very rapid, and this will cause a short electrical current will start flowing. And this electric current will flow down an axon. So here what happens is, notice. So let's divide the axon into 3 parts, okay? 1, 2, 3. So here what happened? At this point, let's concentrate. From minus 70, the voltage changed to 30, and then back to minus 77. So this change in the polarity will cause a short electrical current, a very small electric current to be generated, which will flow a short distance. This will flow a short distance from point 1 to point 2 down the axon. And at 2, what will happen? At 2, again, now what happens is, what is rest will now the potential will change. From where? From minus 70 to 30 and back to minus 77. Again, a small electric current is generated, which will flow a short distance down to the 3rd point on the axon. And again, we will see the same switch of change of membrane potential from minus 30 to, from minus 70, to plus 30 to minus 77 millivolts. And this will again flow to the 4th point, etc. And this will cause, this is nothing but a generation of an action potential. So to wrap it all up, let's see, or to show a graphical representation, as you can see, here's the voltage and here's time. So here the cell is at rest. When the cell is at rest, what happens is the stimulus is coming, and the voltage is minus 70 millivolts. Notice this, and we are, if this is the axon, let's understand we are at point 1, right here of the axon, okay? So here when the message comes and crosses the threshold, depolarization will take place. What is depolarization? Depolarization is when the sodium channels will open and sodium channels enter the cell. So the outside, if you notice, when we were at rest, what was going on? The outside was positive and the inside was negative. With depolarization, what happens is sodium will enter, the inside will become positive in comparison to the outside, which will become negative. So more positive charges have flown in here. Then repolarization will happen, where what happens is the potassium will now leak out of the cell, restoring the voltage back and here to minus 70 or lower, which is the undershoot right here. And here is the refractory period, where the sodium is inside, potassium is outside. This, using the pump, the potassium has to be pumped back in, sodium has to be pumped back out so that the cell goes back into the resting stage. As you can see, so again, the action potential, once it is generated, it will cause an electric current that will flow down the axon, as I mentioned. Okay? So once the action potential forms, it is conducted along the entire length of the axon, From the initial segment, that is, remember, from the axon hillock down the axon to the axon terminal. Here is the cell. Here's the neuron. Here are the dendrites. Here is the axon. So once it's generated here, it will flow the entire length of the axon. In a normal healthy axon that has not been run down by repeated firing, the action potential is always of the same size. It does not decrease in size. So here what I need you to understand is either you get an action potential or you don't. And you don't get little ones and big ones. It's always of the same size. This conduction is non-decremental, at least in an unmyelinated axon. The action potential maintains its full strength along the entire length of the axon and also in all branches of the axon. This is an important concept, all or the non-response, which we talked about a little bit briefly in here. The conduction of the nerve impulse is an example of all or the non-response. In other words, if a neuron responds at all, then it must respond completely. And very important concept, just because the greater the intensity of the stimulation, it will not produce a stronger signal, but can produce more impulses per second. For example, you are taking a nice walk and you see a tiger. So that would be a stimulus of great intensity. So that is not going to create an action potential which is way above 30 millivolts. Okay, it is going to be of the same intensity. It's just that there are going to be more impulses per second. In an animal cell, there are two primary types of action potential. One type is generated by voltage-gated sodium. So the key players are the sodium. And the other is the voltage-gated calcium. The sodium channels are the ones which are much faster, and they will last for about 1 millisecond. So 1 millisecond. The calcium-based action potential, they will last longer, about 100 milliseconds. So with this, we come to the end of action potential, and I thank you for giving me your attention and time.